start the sign-in sheet around, just put an X next to your name and then make sure it gets back to me in the back. So. Okay, welcome to the Friday Transportation Seminar at Portland State University. Today we have three speakers sort of reprising poster or talks that they gave at the Transportation Research Board annual meeting in Washington, D.C., which most of us returned from last night or Wednesday, where there were 11,900 other transportation professionals sharing knowledge. So we have three speakers, Katie Bell, Adam Moore, and Liang Ma, and they're going to go in order. Each take 15 minutes, and then we'll have time for questions at the end. So without any other introduction, I'll turn it over to Katie.
Good afternoon. I'm Katie Bell. I'm a first-year PhD student in transportation engineering here. And what I'm presenting today is research that I worked on in part for my master's thesis. So I want to acknowledge my thesis committee was Miguel Figliozzi, Robert Bertini, and Chris Monsier. And then we also submitted a TRB paper related to a portion of this research, and the co-authors on that were Miguel Figliozzi, Alex Bagazzi, and Adam Moore. I'll give some background on the research to help give some context for the presentation, and then I'll discuss some of the data that was available for the research as well as some of our data collection methods, and I'll review some of the statistical analysis, and then finally discuss our conclusions and suggestions for future research. As you probably know, motor vehicles are the source of a variety of pollutants. I've listed a few here. The one that we focused on the most and that I'll focus on for this presentation is fine particulate matter, or PM2.5. And PM2.5 comes from both non-combustion and combustion sources. An example of non-combustion source is tire wear. And we also collected measurements of volatile organic compounds, but I'm not going to review those results with this presentation. An important definition to keep in mind for this presentation is the definition we use for a hotspot. For this research, we define a hotspot as a subsection of the corridor that consistently has average pollutant concentrations above the 85th percentile when compared to all other subsections on the corridor. This is a graphic that other students at PSU have used for their presentations. It's from the US EPA website, and it gives a good idea of the size of PM2.5. It shows it here relative to the size of the human hair and to beach sand. So it's not the blue dots, but it's actually the tiny pink dots there. Particles less than 2.5 microns or micrometers. So this means they're small enough to be inhaled into the human lung, which is where some of the health issues came from that were listed on the previous slide. The study area for this research was Southeast Powell Boulevard, and as probably most, if not all of you know, it's to the southeast of downtown Portland, and it connects the suburb of Regression to downtown Portland. So it has high volumes of commuter traffic in the westbound direction in the morning and in the eastbound direction in the afternoon. And we studied a 4.6-mile section of this corridor from Southeast 7th Avenue to I-205. One of the main objectives of this research was to develop an efficient method to estimate hotspot locations. We realized that agencies often don't have the resources to collect all the data needed to estimate hotspot locations using some of the programs that are currently available. So we wanted to develop an alternative that required less data and was more flexible in the data that it required. And long term, we hope to better inform personal exposure models and health analyses. This was a fairly new topic for me when I started this research, so I tried to do a pretty extensive literature review. These are the four main categories of the literature review. The one I want to focus on for this presentation is air quality measurements. So measurement methods can be divided into two categories: mobile measurements or stationary measurements. And mobile measurements is what we use for this research. Within mobile measurements, you can consider three different mobile measurement types. what I've seen most often used in the research I looked at was tailpipe or exhaust measurements that give information specific to the vehicle that's being driven. And there's in-vehicle measurements which give indication as to the exposure of the driver to pollution. And then what we used is outside vehicle measurements, which is perhaps the most generally applicable form of measurement, because it's not specific to the type of car that you're driving. Moving on to the data we used for this research, we wanted to look at 4 categories of data listed here, and we wanted to better understand how different variables in each of these categories is statistically related to PM2.5 concentrations. So this slide focuses on our data collection methods. We rented an electric vehicle so that we could limit the impact of the vehicle exhaust to the pollutant measurements. And we drove the corridor a total of 16 times, 8 in the morning and 8 in the afternoon. And then within each of those time periods, we drove 4 times in the westbound direction and four times in the eastbound direction. And this table is the data that we collected. So we collected GPS data for location, and then video footage. We have 4 video cameras to get front, back, left, and right views of the car, which we later used to validate the GPS data and to better understand the different vehicle classifications surrounding the vehicle while we were driving. And then, of course, we collected PM2.5 measurements as well as VOC concentration measurements. And we had, for each of those pollutants, we had 2 monitors, so one on the left side and one on the right side of the vehicle. One of the strengths of this research is the amount and variety of data that was already available for the project from Powell Boulevard. We had access to data from the Oregon DEQ air quality station, which is the red dot in the middle of the map. It's just a block south of the corridor. And then the City of Portland has adaptive traffic signal systems at 12 intersections along the corridor, so we had that data that provided traffic volume and traffic speed measurements, as well as the Wavetronic system, which provided similar information at 2 intersections. And then we had land use data that's available online through the City of Portland, as well as data that's available at PSU that gave information like building height, building setback, building footprint, and then also boundaries of different zoning areas. So moving on to some of our analysis, this graph shows moving average concentrations for PM2.5 across the corridor. Along the bottom, it tells you the street names, and also showing the line for the 85th percentile and the 15th percentile. And this is all study hours combined. And so it includes all 16 runs that we did. And you can see that on average, the highest 39th Avenue has the highest moving average PM2.5 concentration. But we found that within subsections there was a wide variety of concentration. So we needed some sort of measure to also look at the consistency of the magnitudes. So the graph on top is the same as the one on the previous slide. The one on bottom shows how we considered consistency of the concentration. So this graph is showing what we call hotspot frequency. So hotspot frequency is the percent of runs that a given subsection is considered a hotspot. So if you remember the hotspot definition I gave previously, it's the percent of runs for which a given subsection has a concentration higher than the 85th percentile when compared to all their subsections. So if you compare the 2 graphs, you can see that although 39th had the highest moving average concentration, it wasn't necessarily most consistently a hotspot. And then we also created graphs, hotspot frequency graphs for the morning versus afternoon, and it was clear that the hotspot locations were different in the morning compared to the afternoon. So after doing a simple regression analysis and studying correlations between each of the variables with each of the other variables, we did an informed multiple regression analysis to help understand how the variables could be used in combination to predict PM2.5 concentrations. And this is just one example of a combination of variables that can be used. This is a combination that explained the highest percentage of variance of PM2.5 concentrations, and the graph gives you an idea of the relative contribution of each of the variables when the other variables have been controlled for. So this is just one example of combination of variables that we found could be used to estimate PM2.5 concentrations. The takeaway from the regression analysis was that different variables can be used in combination depending on what data is available to the user, the model user. So in conclusion, we found that it's important to consider consistency as well as magnitude and the distance impacted by air pollution. And then morning and afternoon data should be analyzed separately as well as together. I've listed some of the variables that were found to be the strongest estimators of PM2.5 concentrations, but in addition to these variables, we found that after controlling for these variables, land use regression can also help to estimate hotspot PM2.5 concentrations. And ultimately, the multiple regression models, there's flexibility to adjust the multiple regression models depending on what data is available to the user of the models. And we believe that mobile outside vehicle measurements in combination with land use regression is a useful tool to better understand the variability of pollutant concentration levels along a corridor. For future research, we'd like to do a similar analysis looking at cold spots, so areas that are consistently above the 15th percentile for pollutant concentrations. And then also, as I said, we collected VOC measurements, so we'd like to look at that data as well and do a similar analysis to better understand the variability of VOC concentrations. And as I mentioned, it's important to look at consistency as well as the magnitudes of the concentrations. So we'd like to do a regression analysis to see what variables can estimate hotspot frequency, so the actual locations, not just the magnitudes of the concentrations. And then also study outliers to find out what some of the variables were that were causing those huge variations in concentrations. And then also I've listed some other variables that would be helpful to study. So I'd like to acknowledge OTREC and NITSE for sponsoring this research, as well as the Eisenhower Fellowship Program, my thesis committee I mentioned earlier, and the co-authors on the TRB paper we submitted. And I think we're doing questions at the end, I think. So thank you.
Are high emitters certain kinds of vehicles, or
yeah, we considered high emitters. It's basically a dummy variable, so it was just yes or no, they're present, and we considered them bus, passenger trucks, or commercial vehicles. So, yeah.
I was wondering, you've talked about all the different variables that are coming in here, and a lot of them, it's construction, or an underpass being there, the temperature, the air. You know, it looked to me like you had a lot of the same vehicles in adjacent places, but high peaks in some of them. I was wondering if you have any plans to do like any kind of modeling to really understand what's happening with the atmosphere in those areas, that why some areas disperse and some do not?
Well, Adam's presentation might give you some some feedback to that question because his present, I should let him describe it, but it has much more kind of micro view of the areas. This was to get a corridor-wide view because we have research that's looked at the micro view. So we have the DEQ monitoring station that gives some of the atmospheric variables, temperature and wind speed and direction at one location on the corridor, and then also background pollutants. But for this project, we didn't have a way to look at those variables at a corridor-wide level.
Then would you say that this particular research you're doing would interface well with that because you're kind of giving some of an idea of what some of those things might be?
Yeah, so we have talked about looking at how the two approaches can be, how they can build off each other and how we can use them, integrate them to combine the micro and more corridor level views.
Okay, so we'll have the rest of the questions at the end. So thanks, Katie.
Okay, thanks.
So Adam Moore is next.
All right. Hello, everyone, and good afternoon. So I'm going to be giving the presentation that I gave almost exactly 48 hours ago in DC. So you're in for a treat because it's fresh in my mind. What I'm going to be talking about today is a project that we worked on over the summer. It's going to sound a little bit similar to Katie's at the beginning. There's a lot of overlap there in terms of basic concepts and things like that, but I promise you it's original. What we're looking at here is roadside exposure to PM2.5 for people who are either taking the bus or walking on sidewalks, things like that. So whereas Katie's was moving up and down corridors in a vehicle, measuring outside the vehicle, I'm standing in one spot measuring for an extended period of time and measuring a lot of other variables as we do that to try to understand what in that one spot is really affecting our exposure to PM2.5. So to get started, I just want to go over just some background stuff. PSU here has been working on a variety of projects on Powell Boulevard. Katie's project was on Powell. This one is on Powell. And we've been there for a little while. Because Powell is kind of unique, it's a very busy arterial linking downtown to the suburbs. And it's been outfitted in a few different spots with some pretty interesting data collection techniques that I'm going to cover in a second. We've been there for a while, our research team, investigating variations in particulate matter levels. And we're incorporating many different data sources in order to do that. Like I mentioned, traffic, air quality, meteorology like temperature and relative humidity. And we're using statistical analyses to control for many of those factors so that we can really single out the effect of, say, one additional vehicle. How much does that really contribute to the ambient PM2.5 levels? Just to give you a brief background, it's going to sound a little bit familiar to Katie's. There's exposure to air pollution on roadways. That's pretty obvious. We all know that vehicles pollute. We can break down who's being exposed, if we're being very general here, in terms of how you travel. Do you travel by vehicle, public transportation, or are you a bicyclist or a pedestrian? And is there a difference between any of those? These have all been studied a lot. We are focusing on two different things in particular, public transportation and bicyclists and pedestrians. And we're asking the question, what factors affect exposure to air pollution for those people? That's our key linchpin question here. And we're looking at that using three different categories of variables: the built environment, vehicle activity, and meteorological conditions. So we're going to talk just a little bit about that question related to the built environment and dispersion and things like that. Vehicle activity, free flow conditions versus congestion, and then temperature, wind, things like that. What makes this project unique, what is really our contribution to the literature, is that we're using very high resolution data. And this is not necessarily a first, but it's kind of the first in how we're combining everything. We're using 10-second resolution for all of our data, ranging from the particulate stuff to vehicle activity to the weather. So that's our goal here, is to demonstrate what you can see when you use such high resolution data. What can you really describe in the environment? You've seen this already, so I'm not going to go into it too much, but this is PM2.5. It's very small. It can travel very far into your body, through your lungs, and with it, it brings lots of different contaminants. It's recognized by the EPA as a criteria pollutant. It comes from vehicle emissions, brake wear, tire wear, things like that. In terms of, it comes from a lot of different sources, but in terms of roadside what we're concerned with right here. It comes from those three things. It's been linked to a lot of different diseases, ranging from cancer all the way down to asthma. So pretty important to understand where we are being exposed to it. So our study location is on Powell, like I mentioned. I had this for all the people in DC. I think you guys probably all know where Powell is. It's a pretty busy road, 31,000 vehicles daily, up to 1,800 during the peak hours. So there's a lot of vehicle activity on that road. This is why we were interested in it. We set up shop at 26th and Powell, where it says intersection right there. That's 26th. Here's Cleveland High School. Powell Park is across the street. We set up two different temporary stations with equipment on them on May 1st, 2013, from 7 to 9 a.m. And we did 7 to 9 a.m. to really capture that morning rush hour so that we could get a lot of vehicle activity during a short amount of time. And we had two different locations, at mid-block and intersection is what we've called them. And I have mid-block in quotes because it's at 24th and Powell. There's 24th, but 24th sees almost no traffic. So we're treating it as the mid-block location. In other words, it's between two major intersections on the roadway. So I'm only going to be talking about mid-block today. Intersection is still under a little bit of work, so I'll save that. To give you a feel for what the area looks like right there, if you haven't been there in a little while, this is the view, a panorama from the north end looking south on the top there. Here's a bus stop right here. And here's a little plan of what is going on. And I have monitoring location labeled right there. That's where we were standing with all of our equipment. And that's a general layout of the roadway right there. So it's a slightly bigger roadway with a lot of traffic on it. This is a picture of our sampling equipment. You get a feel for what it looks like. We have a portable table right here with all of our air quality equipment set up on it. This is a tube running from our particulate matter monitor up to about 5 feet tall so that we're getting that breathing level where people usually, or the average person is breathing, I suppose. This is our, well, I'll cover this right here. So this is what we were using to measure PM2.5. It's called a dust track made by TSI. It's a pretty standard piece of equipment. We are measuring wind and temperature and relative humidity using these two pieces of equipment. So we get wind speed, wind direction from our sonic anemometer right there. It's very futuristic looking. We also had video cameras set up on this pole right here looking at the roadway and at our station so that we can monitor and then go back and reference later on after we've left the site. If we see anything interesting, any spikes in pollutants, we can go back and look at the video. Finally, across the street, it's a little hard to see. It's this little white thing on that pole right there coming down the pole. This is set up by the Portland Bureau of Transportation. They gave us access to it. It was very nice. This is called a Wavetronics smart sensor. And what it uses is radar. It's flashing radar across the street. And with that radar, it's able to tell when vehicles are passing. And we get a lot of information from that. We get the vehicle volume, obviously, speed, classification. So it can tell how long a vehicle is. And using the length of a vehicle, we can guess whether or not that vehicle is a truck or a delivery truck or a car, which is important because those things emit PM2.5 differently. Diesel engines emit a lot more PM2.5, so we want to be able to single those out. It can also tell us lane occupancy, the percent of time during its 10-second interval that the lane is occupied, which gives us a feel for congestion. So I want to talk a lot about that. That was really what makes this project a little bit special, is the kind of information we were able to get from the Wavetronics. This is a view for the entire day on May 1st, 2013, from midnight to the next midnight. We have vehicles per minute on the top. We have speed in the middle, and then we have occupancy, that percentage of time during the 10-second interval that the lane is occupied. So this really gives you a picture for the entire day of what was going on that day. I have a little rectangular box on each of these to show you when we were standing out there. And you can see that while we were out there, there was a pretty substantial breakdown in traffic flow during that time. A lot of congestion that day. So it was even more congestion than some of you may be accustomed to if you travel on Powell. This was backed up very, very far. It was a parking lot. So that was a good and a bad thing. It was interesting for us to really be out there when traffic is at its worst. And that's really good. It's bad because we were breathing it while we were out there. To give you a little more idea of what we want to do with that information, we can see a lot when we have such small resolution. We can really look at vehicle platooning in particular. And what I mean by platooning is when vehicles are released from the upstream signal. So when a green light and you all move through as a big pack of cars down the corridor, that's called platooning. And we have signals at 21st and 26th. Sorry, yeah, 26th right here. They are both running at about 125-second cycle lengths. So every 125 seconds, we should see a pack of cars moving through in the data. And we can do that. We can look at that by using correlation functions. These are autocorrelation functions and partial autocorrelation functions I'm showing you right here. And that just means the present observation of vehicles correlated with previous observations of vehicles. And we should be able to see that they were correlated with vehicles every 130 seconds, 120 seconds. And what I have right here are red arrows at 130 seconds. The blue line is the significance, so if it's taller than the blue line, it's statistically significant. And we can see that we were able to very clearly picture vehicle platooning in our data. And that's pretty exciting because we can use that information then, and we can correlate our vehicles platooning with the PM2.5, and hopefully we'll see some kind of significance there, some kind of activity. And we do that using cross-correlation functions. Every time the vehicles went through, we correlate it with the PM2.5, and again, the blue line is the significance. So our westbound cross-correlation function here, we didn't have anything that was significant, which isn't necessarily surprising because it was a parking lot, so there's not a lot of variation in that for the data to match with. However, on the bottom there, eastbound was free-flowing for the majority of the time, and we are able to see a pretty strong thing right there. That's at 130 seconds. So that means that our platooning is significantly showing up as a predictor of PM2.5, or it's significantly correlated with it. That was something that you can't really show with any data that is aggregated to larger than the cycle length. So if you have data that's at 1 minute, 2 minute, 3 minute, you have to have something that's less than 120 seconds in order to be able to see that. So that was pretty neat. That's a neat contribution of our high-resolution data. So we did not see it for westbound, but we did see a significant effect on PM2.5 for our eastbound direction. We expect that we would also see it westbound if it had been free flow that day. So now looking into it a little bit more, we have our westbound and our eastbound columns here. And I'm showing you on the top row a cumulative volume function. So I'm just adding vehicles up, just adding all the vehicles throughout the study period. And so our westbound direction, you can see right about here, there's a shift in the vehicle arrival rate. And what we can do with that is amplify that line. So this line on the bottom row is just this line kind of amplified to make it more clear. And right here at 7:38 and 20 seconds, the line suddenly shifts. And what that means is that congestion arrived. Congestion started right there in front of our spot at 7:38. So we know that anytime after that, the road's going to be congested. Anytime before that, the road was not congested. And we're going to look at that in terms of how did the PM2.5 concentrations change before and after the onset of congestion. And we do that by looking at active queuing, or we look at queuing. So when vehicles are queued up, it usually means that the road is congested. And what I have here, every gray bar is when vehicles were queued. And we get that information from this curve. So what I'm going to show you now is the PM2.5 before and after congestion when vehicles were queuing for those two respective phases. So when they are queuing, which I call active queuing, when they're actively queuing before congestion, we actually see lower median concentrations of PM2.5. But after that onset of congestion, we see much higher median concentrations of PM2.5 during queuing phases. So there's a lot of stuff to read into that. If it's 11% higher during congestion when vehicles are queuing, that's confirming. It's a little bit obvious. Everyone knows more vehicles crammed into a tiny space. In other words, when they're queuing, is going to create more pollution. But now we're able to quantify that, and that's very exciting. As for the pre-congestion queuing, that's something that we're still theorizing with. That can get into some more complicated interactions between the vehicles and the dynamics on the roadway. So vehicles are tapping their brakes, which is activating the queuing, but it's not lasting very long because there's no congestion. So what that actually could mean is that vehicles are just slowing down just a little bit, then slowly going forward again. They're not stopping all the way to 0 miles per hour and then slamming on the gas again to accelerate and things like that. So we're still working on describing that, but it's a very interesting outcome from our data. So finally, last thing here, I want to show you some results from our linear regression model. We modeled all of our data to try to really control for different variables. And I have a very simplified version of it right here for you just to show you what was expected to increase PM2.5 levels and what was expected to decrease PM2.5 levels. The larger the font, the more effect that variable had on our PM2.5. So vehicles passing when wind blows across the roadway towards the monitoring station, so it's bringing all that pollution across the roadway towards where we were standing. Current and previous observations of that were shown to increase PM2.5. And we can quantify that. We have those numbers. I'm just not showing them to you right here in the sake of simplicity. As relative humidity increases and obviously as congestion worsens, we are seeing higher PM2.5. And then wind from various locations, wind speed, wind direction is going to lower the PM2.5. which makes sense. It's clearing out the area. Last thing here, SEMI-ELASTICITIES we got from that model. We're able to say the variable lagged by what changes PM2.5 by how much per unit. And what I mean by lagged is we have a current observation of a vehicle. How long does it take before that vehicle's passing, before we see the effect of its emissions? So occupancy as the 1% increase in occupancy over 10-second interval change PM2.5 by positive 0.05%. And further on down that table. So that was pretty interesting. So in conclusion, what we're looking at here is exposure to roadside fine particulate matter. We're doing a pretty unique thing here is we're really demonstrating what we can do with data availability by showing platooning and congestion, two things that you would really need high resolution data to be able to see, and we're getting some pretty interesting results from that. This can be useful for model calibration for existing models that are already out there. If we're able to show some pretty fine-grained, minute changes in traffic affect PM by what percentage or degree, then we can use that to calibrate existing models and make them even more accurate, which comes in handy for policy to help everyone breathe better air. So with that, I want to thank OTREC for funding our work and my co-authors, Miguel Figliozzi and Alex Bigazzi. And I don't know how I did, but we might have time for questions. Ask a fast question.
So, wasn't really the point of your talk, but how fast can PM2.5 change? I mean, you had this very fine granularity. How much change would you see in 10 seconds or a minute?
That has a lot to do with your sources and your dispersion. In other words, if you have a large truck go by that's just belching emissions, then you're going to see a pretty quick change once that reaches where we're standing. And it also has to do with the way the wind is blowing. If the wind is blowing away from us really strongly, then it's going to clean out the air. It's going to take that truck's emissions elsewhere, so we're not going to see that change. However, if it's blowing towards us, we're going to see that change even faster. So that's a tricky question to answer because it can change very quickly or it can be stable throughout the day, depending on a variety of environmental factors and source factors.
I was sort of curious if between one reading and the next you could see like a 50% difference or...
Anecdotally, I don't think we ever saw anything like that. I would have to check, but it's rare that you'll see, unless, well, all things being constant, it's rare that you'll see a big change. But if a big source emitter comes into the scene, you will see a big change. But I can't tell you how much, 50%, 10%. It depends.
Okay, good afternoon, everyone. My name is Liang. I'm a PhD candidate in Urban Study at Portland State University. So the cause of this study is Professor Jennifer Deal. So this study is about the correlation between the building environment and people's bicycling behavior. So this study focuses on the different effects of the objective measure of the environment and people's perception of the environment. And bicycling for transportation, not include the bicycling for recreation. So some brief introduction. So in recent years, there are a growing number of studies that link the building environment with active travel behavior, including both walking and bicycling behavior. And among this study, there are two types of measures are commonly used. The first one is a perceived measure, and the second one is objective measure. So the objective measure is usually derived, calculated based on the GIS or the audit tool, and the perception measure are usually derived from the household survey, or travel survey, or the interview. So many studies actually use these two types of measures interchangeably, but few studies actually have questioned whether these two types of the measures correspond to each other. So this map to show how our perception of the outside environment is formed. So we perceive the outside environment through our primary receptive senses, such as sight, smell, hearing, taste, and touch. And all this in sensory inputs are then integrated to form our cognitive representation of the outside environment. And during this process, there are a lot of factors, including both individual and social factors, can influence this process. For example, a female may perceive a bicycling environment differently than with a male, and a frequent bicyclist may perceive a bicycling environment differently from a non-bicyclist. So the purpose of this study is to test the different effects of the objective and the perceived environment on people's bicycling behavior. So the data for this study is from a random phone survey in Portland, Oregon, which was conducted in 2011. And the overall response rate was 20%. So based on this survey, we actually derived 4 pairs of the building environmental factors. So on the left is the perception measure, which was derived from the survey. So the first 3 is about bicycling infrastructure, which includes the bike trail, bike path, bike lane, and the quiet street. And the last one is about the bike destinations. So we tried created different methods, objective methods, using GIS to correspond to the 4 perception methods. For example, for the first pair, the perception method is to ask a respondent to assess whether there are off-street bike trail or paved paths in or near their neighborhood, using a Likert scale from 1 to 4, from strongly disagree to strongly agree. We created different types of objective measures, such as miles of off-street bike paths within 1/8 mile, quarter mile, half mile, and 1 mile buffer, both circular and network buffer, and also the distance to the off-street bike path. So we created a similar objective method for the bike lane and the quiet street. And for the bike destination, we use the number of retail jobs within different buffer size. Initially, we calculate the associations with these different types of objective methods and the perception methods. And finally, we keep to use a half-mile circular buffer for the objective method because they have the highest associations between with the perception method. Even though when we ran the correlation between the perception method and the objective method, we found the correlation coefficient was very low, most of them below 0.2. So this is our model bicycling behavior variable. So we have 2 variables. The first one is to predict whether people bicycle or not during the past months. And the second one is if they did bike, how many days they bike during the past months. So the first model, we use a binary logistic model. The second one, we use a multilinear model. For these 2 dependent variables, we actually run 4 separate models. So the first models, we have social demographics, and also just includes the perceived environment. And second one, we have the social demographics, and only have the objective environment. So we want to compare the different effects of these 2 types of measures by comparing the results of model 1 and model 2. And in the third model, we included the 2 types of measures simultaneously. And in the model 4, we further controlled for the attitude and the social environment. So this is the results for the first dependent variable, which is whether people bike or not during the past months. So we can see the social demographics variables, most of them are significant and have expected sign and are relatively consistent among the 4 models. For example, the elder people, female, are less likely to bike, and the people who have the general good health condition are more likely to bike. So I will focus on the building environment variables. For the first model, we just have 1 perception measure of the building environment was significant, which is the back destination, perception of back destination, which was positive and significantly correlated with the bicycling propensity. But its objective measure or back destination in the model 2 actually was not significant. Similarly, the objective measure of minor streets in the second model was significant, but its corresponding perception measure in the model 1 was not significant. When we include these two types of measure in the model 3, we can find that that previous two significant variables was retained significant in the third model when when the model controlling for their corresponding measures. So it indicates the two types of measures may have some independent effects on people's bicycling propensity. So in the model 4, we further controlled for the attitudes and the social environment. We can see that we are interestingly we controlling for attitudes and the social environment. Most of the objective building environment variables become significant, and they have expected sign except the number of retail jobs, which was negatively associated with the bike propensity. We explain this unexpected results like because we measure this variable using a half-mile buffer. So if there are many bike destinations within a half-mile buffer, people may also choose walking rather than biking to this destination. So there may have some competition between the walking and the bicycling. May have to explain the negative sign of the retail jobs. Also, we can note that from comparing the Model 3 and the Model 4, we can see the R-square increase a lot in the Model 4 by adding the attitude and social environment variables. So this indicates that attitudes and the social environment may play a much stronger effect on people's bicycling propensity. So similarly, we have the bicycling model for the bicycling frequency. This is to predict how many days they bike during the past month. So similarly, most of the social demographic variables are significant, have expected sign, and consist among the four models. For example, the elder people, people who have children, female are less likely to bike more frequently, and people who generally have good health condition bike more frequently. So different from previous model, in this model, most of the building environment variables become significant, either using the perception measure or using the objective measure. For example, both types of measures of the quiet street and the bike destinations are positively and significantly correlated with the bicycling frequency. However, we found a very surprising one, that is perception of strict bike paths is negatively associated with the bicycling frequency. However, its objective measure amounts of strict bike paths is positively associated with bicycling frequency. We explained the negative association between the perception of strict bike paths and bicycling frequency may have two possible reasons. One is the frequent bicyclists may be more concerned about the problem associated with the bicycle infrastructure within their neighborhood, and also the occasional bicyclist may overestimate the presence of the off-street bike paths within their neighborhood. This is two possible reasons. So when we have these two types of measures in the Model 3, most of them actually retain a significant. This also indicates they actually have independent effects on people's bicycling frequency. So in the Model 4, we further controlled for the attitudes and the social environment. And in this model, social environment was not significant, but the attitudes still are very significant, and by comparing Model 3 and Model 4, the R-square increased 10%, which is also a significant increase from the Model 3. This, again, indicates significant effects of attitudes on people's bicycling frequency. So summarize some main findings. So from the two models, we can find that the perceived and objective built environment have independent associations with bicycling propensity and bicycling frequency. And the models with both types of measures actually explain more than the models with just one or the other. And attitudes and social environment may play a very stronger role on people's bicycling behavior, and therefore interventions on changing people's attitudes and encourage a supportive culture on bicycling is very important. So based on this, this is the conclusion of this study. So promoting bicycling behavior cannot rely on one solution. We need a combination of different interventions. So traditionally, our urban planner focus on the changes of the built environment, the actual built environment. But this study also found the independent and significant effects of people's perception of the environment on people's bicycling behavior. Also, the attitudes and the social environment also play a very significant role. So besides our traditional urban planning and design interventions, we should have some interventions on changes people's perceptions, such as marketing program and public bicycling events, such as cyclovias and the City of Portland Sunday Parkways, which may help to increase people's perception of their neighborhood environment. Also, some intervention program aims to change people's attitudes and the social environment, like the bicycle education to the children at their early stage to help them to form a positive attitude towards bicycling is also very important. Yeah, finally, I want to thank you, my co-author, Professor Jennifer Deere, who helped to review and interpret some model results. And we also thanks funding support from OTREC and the City of Portland. Yeah, that's all. Thank you.
So we have some time for questions for all three speakers. So if you could all three go back up and share the mic. And before you ask your question, make sure you say your name so that I can
I had a question for Katie. You said that when you controlled for some of the other variables, that land use planning emerged as one that had some impact. What were some of the land uses that were associated with like lower impacts or higher?
Yeah, so just to clarify, the land use variables we looked at were percent zoning, so percent of industrial. We looked at industrial, residential, and commercial impacts, and then also building height, building setback, and building footprint. And none of them had a strong statistical relationship with PM2.5 concentrations, especially when you compare them to some of the other variables we looked at, like traffic speed and traffic volume. But after controlling for those other variables, like traffic speed and traffic volume, depending on the model that we were looking at, adding some of those other land use variables, I think residential zoning shown to increase the power of the model. Those variables did have an impact. So residential, I know, was one that a higher percentage of residential zoning was associated with lower PM2.5 concentrations. But those variables are also somewhat, there's some correlation between, for example, residential zoning and traffic speeds. So that's what the multiple regression models were for, to some extent, to control for the traffic and speed, those types of the traffic variables before adding land use variables into the model.
Okay, my name's Ian Galloway, and this question's for Adam. I was just wondering, did you discover any solutions to lowering the PM2.5 levels on Powell while you were I know that you mentioned that there's you guys talked about platooning and everything, and just during that time of the day that you were there, it looks like it's quite a bit of traffic. Did you was that part of your project too? Is also just kind of like looking at possible solutions in the future? Is that kind of, or did it allude to any solutions to lower PM2.5 levels?
I think that's a really good question. So a lot of what comes out of stuff like this, like what we did, is not so much finding new solutions as, in a lot of ways, and this sounds really bad, but it's kind of like confirming the obvious. So clearly more vehicles is more pollution. I think we all could say that, and we don't all study air quality. But the goal of stuff like this and what we're really able to get out of this is to quantify that. So what is that contribution? Like, how much worse is it when we add one more vehicle? And then when we ask that question, it immediately gets a lot more complicated. Well, it depends which way the wind is blowing. It depends on the temperature. It depends on the built environment. So I can't say that we actually walked away from this with a new bright idea on how to solve the problems. But I could say that we were able to show that one additional truck, heavy vehicle as we call them, is a lot more damaging to the air quality than one additional passenger vehicle. So maybe if we move those trucks to a different roadway where there aren't as many people on the sidewalks, then we're minimizing and mitigating that exposure. So that's the best way to answer your question, is we can confirm some other beliefs.
Jennifer, so my question's for you to build on that. Did you look at any similar studies that presented any other data for the seasonal variability, say December, November, heavier traffic times of year versus May?
Yeah, we did. We looked at a lot of other studies in the build up to this project, and I can say that there is absolutely a seasonal difference, especially in places like Portland, where you have pretty strong seasons. So the summer is pretty hot, the winter is pretty cold, and that affects all kinds of the mixing height of the atmosphere changes. And so as the mixing height lowers, we see higher concentrations because it's kind of squishing everything down, and that we have inversions where the atmosphere is. Those are the kinds of days where you go up to Mount Hood and it's warmer than it is here in Portland, and things like that. So that's going to affect the concentrations too. So our May 1st data collection comes with the big caveat that it's 1 day for 2 hours, and that is not going to pass muster for, say, building a whole new policy for the EPA, but it's going to be perfectly sufficient for what we were doing, which is building our regression model off of a small sample of high-resolution data. Patrick?
Patrick, this is a question for Liang. Do you have any sense of whether there was a group of people whose perceptions of the built environment more closely matched the objective measures of the built environment than maybe another group of people, say, those with pro-like attitudes or those who cycle for? Do you have a sense of that?
Yeah, that's a very good question. So actually, I'm right now working on another project. Also one of my dissertation paper is to explore what factors contribute to the mismatch between the perception and objective measures. I don't have any answer for your question, but I think there are different, for example, social demographic variables like gender, income, education, and also their attitudes, pro-bike and not pro-bike, and also their behavior, people bike or not, or they work or not. All these factors can play a role, contribute to the mismatch between the objective perception measures. Yeah, thank you.
My question's also for you. My name is Nicholas Coble. The number of retail jobs negatively affected whether people bike for transit in that table.
Yeah.
I think you mentioned why, but I was wondering if frequent transit stops or whether people lived closer to the downtown district might have played a role in in that?
Possibly, you mean the spatial distribution of those people who live in the downtown area? You mean the cluster? I'm not.
Right. So if someone's living in downtown,
Yeah.
maybe they feel that the streets aren't conducive to biking, and that would affect whether or not they bike. But there are also a lot of retail jobs in downtown.
Mm-hmm.
So I'm just curious if downtown itself was maybe an outlier, whereas more toward the periphery, you have places with still maybe perhaps large number of retail jobs, but bike infrastructure is a little less intimidating.
Yeah, you're right. Yes. So probably, there are probably some factors we may not controlling in these models that is associated maybe downtown effects, but we didn't consider those effects in our models. Yeah.
And can you repeat then what you thought?
Why we? Okay. Yeah. So we calculate this objective measure of retail jobs using the half-mile buffer. It's just maybe 800 meters. So I think people. So if there are many back destinations like a grocery store or a restaurant within their half-mile buffer, people can easily walk into those destinations. They may not choose to bike to those destinations. So within this area, so walking is a competitor for biking. So that's maybe explain the negative associations between the number of retail jobs and the bicycling behavior. Yeah.
My name is Abhinav Mishra. I have a question for Adam and Katie. So you guys did your research on Powell Boulevard, right? And so is there any research done for people around living around the hotspots area and who are actually more prone to get diseases? Maybe rush hour timing, so it will help us designing better traffic flags, so we don't want a traffic congestion close to residence areas, because if they're getting heart disease because of this PM2.5, we really don't want that platooning happening, near residential areas. So I was just wondering if there's any research done by around the hotspots area, people are actually getting more heart diseases in this section on 39th Avenue, or there's a, you know what I'm saying?
So that's a pretty interesting point, and it really relates to the concept of environmental justice, and so where people live and how that is going to affect really basic things like the air quality. There's a lot of research saying that the closer you live to highways is worse from an air quality point of view, and that gets back to this exact same stuff with Powell. Powell's a bigger roadway, and highways are even bigger than Powell, so there's going to be even more pollution. There is not any movement in terms of policy making or things like that that would really, an air quality backed policy that would really promote using that as a factor for where you live, for where we build housing developments, where we zone residential, things like that. There's nothing like that. So as a little aside, there's a really interesting thing that one of the professors in environmental science here at PSU, Linda George, brought up that I remember from a long time ago. So the Pearl District is a really upscale development now. It used to be a little run down. Now it's very upscale, and it's actually going against the general trend of where people would choose to live in proximity to highways. So people in the Pearl District live really close to highways because 405 is right there. And that is kind of interesting because the air quality is going to be worse. So this is an instance where it's typically lower residential living close to highways, which means lower income is going to be exposed to more pollution. Now we see higher income exposed to more pollution. So it's a little bit of a flip-flop. And that might speak to a changing in terms of how we need to address that.
I guess I just add, and maybe Adam could build on this as well, because he might know more about this area than I would. But something I'm just starting to learn about is the change in concentration levels from on-road to as you get further from the street. And so I think it's important to take that into account too. Maybe Adam has a better idea than I do of how much it changes from the street as you get further from the road.
I'll add to that just really fast. Yeah, we do see a gradient as you get further away from the roadway. So there's a pretty substantial drop-off. I think it's 150 meters. You lose 50% of the concentration. And that is going to affect if housing setbacks and things like that. Yeah.
Like in terms of like traffic signal.
All right, well, let's thank our speakers one more time. And next week we have Professor Sal Hernandez from Oregon State University. He's a new faculty member there. He's going to be talking about modeling injury outcomes related to truck crashes. And as part of that, we'll have a small lunch with him. So if you're interested in that topic or interested in meeting with him, send me an email and I'll see if I can get you. It's a hosted lunch, so we have some sandwiches. So if you're interested in that topic and you want to have some time with Professor Hernandez, just send me an email. So other than that, we'll see you next week. And make sure you turn in your questions if you didn't get a chance to ask one. And also, don't always write a question. Try and ask a question sometimes. So, all right.